Good afternoon, everybody. Let's get started with the last lecture of the course. For announcements, there will be an exam, the final exam, on Tuesday, May 6th. That will be from 7:30 to 10 p.m. You can double check that on the university's final exam schedule. I will send an email about or a Canvas announcement out about this, but in general, the exam is cumulative, but it will concentrate on op amps through the end of the course. So you can see the PDF schedule on Canvas that has all of the topics listed. So from op amps through the end of the course, that's what the exam will concentrate on. But of course, op amps and other topics rely on the earlier course material. So you still have to understand node voltages and Ohm's law and KVL, KCL. So keep that in mind. There are review problems posted. There are also practice problems that walk you through some op-amp problems and some other topics. So be sure to take a look at those. And then we're going to work review today, review problems, and I will post those slides. And you'll also have a video of this review. And then all lectures are posted for a review. If you want to go back and look at the video index, you can find topics and watch the video. Watch a specific topic. If we don't get through all the review problems today during this lecture, I'm actually going to continue into the office hours time period. If you want to make that, great. If not, you don't have to stick around. I'll post the video if you want to watch the remaining review problems if we don't get to those. Okay, so let's jump right into it and start talking about the specific topics to start out with. So operational amplifiers will be covered on the final exam. We talked about linear circuits using op amps. The linear op amp circuits have, let's see, they have negative feedback. So if you see negative feedback in a circuit, then it's a linear op amp circuit. If you don't see negative feedback, it's a comparator circuit, okay? And so then we covered digital electronics, digital systems. We talked about numeric data. We talked about combinatorial logic to build circuits that can make decisions based on present inputs to give you a digital output. We talked about microcontroller concepts and digital ports and a little bit about peripherals like analog to digital converters. And then we finished up talking about electric motors. We talked about DC motors. We talked about the components of a DC motor, what the vocabulary is, how they basically work. We talked about control of DC motor direction and speed. And then we moved on to stepper motors. We talked about how to control a stepper motor, what they are, how you can use them for precision, angle, and speed control. And we finished up with servo motors. So that's primarily what the final exam is going to focus on. Again, generally it's cumulative because these topics depend on earlier topics in the course. So I'm going to run this review as a set of clicker questions. So get your clicker app out and we'll just get started solving some problems, starting with op amps and then going into the motors topic. So here is your first problem. Okay, so you have this op amp circuit. And the input voltage is Vin, the output voltage is Vout. If Vin is 2 volts, what is Vout? And again, whenever you don't see an op amp powered with VCC and VEE, just assume the op amp is sufficiently powered. Okay, so give this a shot. And I'll give you a hint, you shouldn't have to take too much time on this. The circuit should look familiar. So take a minute and try this. So you shouldn't have to work too hard at this one. If you look at the circuit, it should look familiar. Remember, I talked about the decision tree, how to analyze an op amp circuit. And if an op amp circuit has negative feedback, and this one does, you can identify that because there's some connection between the output of the op amp and the inverting input where none of the nodes in between are held at a constant voltage, that lets the output voltage of the op amp influence the input differential voltage, and specifically the node voltage of the inverting input. And if you see negative feedback, you either have to use the negative feedback approach and analyze the circuit. You assume that the input differential voltage is 0 because of negative feedback, and you assume the input currents into the op amp are 0 just because it has generally high impedance inputs. So you use that approach, which is the long way, or the short way is the common circuit approach. If you've analyzed a circuit before and you recognize it, then if you know the gain, or you can calculate the gain, if you have an input, you can calculate the output voltage. So in this case, I recognize the circuit because of the connections drawn here. We talked about this one during a lecture. And so this is a non-inverting amplifier. And the output is equal to 1 plus the feedback resistor divided by that resistor that goes to ground. So 1 plus 4 is 5. The gain is 5. And so 5 times 2 is 10 volts. Okay. All right. So that's a type of circuit you should know. Let's move on to another circuit. And if you have any questions, throw them up in the chat. I see a question about a review on Monday. No, there's no review on Monday, but I'll continue into office hours today. And if you have any questions, you can ask them, or you can post questions on Slack under the exam channel. So I'd be happy to answer them there too. Okay. So here's another op-amp circuit. This circuit has an input node voltage and output node voltage. If V out is 4 volts, or V in is 4 volts, what is V out? So this is another one of those circuits where you should recognize it. First, we try to identify, does the circuit have negative feedback? I claim it does because there's some connection between the output and the inverting input where none of the nodes in between are held at a constant voltage. So this circuit has negative feedback. And then you try to decide, is this a common circuit that I've seen before? I would claim you've seen this before. This was the first op-amp circuit we talked about. It's an inverting amplifier, and the gain of an inverting amplifier is minus the feedback resistor divided by that series resistor that's in series with the V in voltage. So the gain is minus 0.25. That would give you 1 volt at the output. So 4 volts times minus 0.25, negative 1 volts at the output. All right. All right, let's try another op-amp circuit. This one might look different, but I'd encourage you to look closely. So let me give you another hint here. If you look at this circuit, the input voltage is connected to the non-inverting input. I see a resistor connected between the output and the inverting input of the op-amp. There's a feedback path there. And then there's this resistor that goes between the inverting input and ground. And then the output has a load resistor on it. Okay. So if I were to redraw that circuit in a little different way, right? You could convince yourself this is the same circuit. So this might influence your answer. Right? There's a 12K ohm resistor between the output and the inverting input, just like there is here. V in is applied to the non-inverting input. There's a 3K ohm resistor between the inverting input and ground. And then the output has a load resistor connected to ground. All right. All right, let's talk about this. So this is the second op amp circuit we talked about in the section on op amps in this class. So this is a non-inverting amplifier. Non-inverting amplifier has the gain of 1 plus the feedback resistor divided by that resistor that goes to ground. And so the gain is 5. Okay. All right. Let's try one that takes a little more analysis. So give this one a shot. You might have to copy this one down and work it. So I'll give you a few minutes on this. All right, let's start talking about this problem. So when you see an op amp circuit, first identify, does the circuit have negative feedback? And here I see a connection between the output of the op amp, right? The output of the op amp and the inverting input through this 1K ohm resistor. And neither of the nodes on either side are held by any source or a ground to a node voltage. So the output of that op amp can influence the inverting input's node voltage. Okay, so if you see that the op amp circuit has negative feedback and you don't recognize the circuit, we have to use the negative feedback approach, which is this. You assume that the input differential voltage is 0 between the op amp inputs, and that you have 0 amps going into the inputs of the op amp. That's not due to negative feedback. It's just that typically the op amps we use have high impedance inputs. Okay, so we start there. And then I like to just start filling in what I observe about the circuit to see if there's some way I can write a KCL equation or a KVL equation to find V out, right? We're looking for V out here. So I notice that I have a source here that is connected directly to ground. So I can figure out the node voltage of this node right here, right? The node voltage is negative 6 volts. I see that there is 0 volts between the two op amp inputs, right? So between this node and this node, I have 0 volts. So the node voltage between this node, or the node voltage of this node, equals the node voltage of this node because there's 0 volts between them. So I can say that this upper left node has a node voltage of negative 6 volts as well. Okay, with that, I could say, well, I could figure out the current through this 2K ohm resistor. I have negative 6 volts here, ground here. That means I have 6 volts across that resistor that would cause negative 3 milliamps to flow down, right? Okay, so now I'm starting to get somewhere because I see that I calculated the current through this branch. I have given to me the current through this branch. There's no current going into the op amp. So if I have 5 milliamps coming up here and I have equivalently 3 milliamps coming up here, negative 3 going down, positive 3 going up. So 5 going up, 3 going up, all of that current must go through this 1K ohm resistor. So 8 milliamps must go through there. If I have 8 milliamps through a 1K ohm resistor, I have 8 volts across that resistor. So I've figured out a lot of different values around this circuit. V out, if I write the polarity of V out, it's between this V out node and ground. Okay, so then what I can do, I think I have enough information here to write a Kirchhoff's voltage law equation. Let's say start here, I could say minus negative 6, minus 0, plus 8, plus V out equals 0, right? So minus negative 6, minus 0, plus 8, plus V out equals 0. So V out is then negative 14 volts. Okay. So that's typical of an op amp circuit with negative feedback where You just don't recognize the circuit. If I go back to the previous problems, if you didn't recognize this as a non-inverting amplifier, you could have just solved it like we just solved that last problem. If you didn't recognize the inverting amplifier, you could do the same thing. You could start writing KVL, KCL equations. I'd recommend a KCL equation at the inverting input. That's what we did in class. And you can figure out the gain of the amplifier, or given a V in voltage, what's the V out voltage? Okay, so you can use that negative feedback approach even for the common circuits. It's just faster if you recognize the circuit. Okay.
Can you explain how you got the 8 millivolts again?
Let's see. Which for this most recent problem, this one here, or the
Yes.
previous? Okay, this one. Um, oh, how I got the 8 milliamps here?
Yes,
So,
sorry.
yeah, yeah. So, yeah, let me draw this out here. So so coming up this direction, I have 5 milliamps, right? Because that's coming in through that source. From this 6-volt node voltage, so I have, let me write the polarity in here, plus minus, I have minus 6 volts. Let me try to write a 6 there. That's minus 6 volts with that polarity across that 2K ohm resistor. And that means I have negative 3 milliamps going down. I could also say if I have negative 3 milliamps going down, I have plus 3 milliamps going up, right? So 3 milliamps coming up into this node, 5 milliamps coming up into this node. That 8 milliamps, 3 plus 5, has to leave somewhere. You have 0 going into the op amp, so that 8 milliamps must be going this way. Okay. Um, the sum of currents entering a node equals the sum of currents leaving a node. That was a long way to say Kirchhoff's current law. Okay. And then once you know that 8 milliamps value, you can calculate 8 volts across that resistor with that polarity. Okay. So someone says in the chat, wait, if we can't conclude that it's a non-inverting or an inverting op amp, we can use KVL. Yeah, you can use KVL, KCL, Ohm's law, just like we're doing here. If you can't figure out what an op amp circuit is, what its maybe common name is, and what it does, then you can use the negative feedback approach just like we did here to figure out whatever you're looking for, either the output voltage or some other voltage, or the output divided by input voltage, which is gain. So, all right. Okay. Any other questions on this one or the earlier problems?
How would you do the KCL on this one?
Um, let's see. The KCL that I did, oops, the KCL that I did, if I get my pen back, was at this node, right? So if I were to write a KCL, it would be, hey, I wonder if I can write this here. So here my KCL is, let me sum the currents, let's say entering the node. And let's call this current that goes left to right through the 1K ohm resistor, let's call that like IX. If I sum the currents entering the node, I would say 5 milliamps plus, let's see, sum the currents. I have minus negative 3 if I use that current, minus negative 3 milliamps, right? So 5 entering, negative 3 is leaving, so positive 3 is entering, and then entering would be minus Ix equals 0. So sum the currents entering, set that value equal to 0. So that would be my KCL at that node. All right, other questions on this or the previous problems. And if you want to see how to derive the inverting amplifier gain or the non-inverting amplifier gain, we went through that in detail. You can see that lecture. It's posted under the video section on Canvas. Okay. Let's see. Let's try. Not that. Let's try this one. So I'll give you a hint on this, right? We're trying to find V out. If you look at this op-amp circuit, ask yourself, does it have negative feedback? Is there some connection between the output and the inverting input that doesn't have a node that is connected to a constant voltage? Right? Remember, for negative feedback to exist, the output has to be able to influence or change the voltage at the inverting input. And if there's no negative feedback, then it's a different type of circuit. It's not a linear circuit. All right, let's talk about this. So I pointed out there is a connection or a path you could follow from the output to the inverting input. But this is not negative feedback because this node at the top is held at a node voltage of 10 volts, right? There's some source that's not shown here. It's implied. There's some source that is holding this top node at 10 volts. So even though the output voltage may change, that output node voltage may change, it doesn't influence or change the node voltage at the inverting input, okay? So that means there's no negative feedback here. Okay, so we've identified that. So that means that this circuit is not a linear op-amp circuit, it's a comparator. Okay, so that means we have to look at or calculate the voltages at the op-amp inputs and decide what is the output voltage based on the comparison of those two inputs. So here we have 4 volts node voltage applied to the non-inverting input. So V1 is 4 volts. V2 is determined by voltage division. We have 2 series resistors here, 2 3K ohm resistors. And we're looking for the voltage across this bottom 3K ohm resistor, right? These resistors are in series because the same current goes through them. The same current goes through them because no current goes into the op-amp input approximately. Okay, so by voltage division, you're going to get half of the voltage, half of that 10 volt source across this bottom 3K ohm resistor. So that's where you get V2 equals 5 volts. And remember that you're comparing the voltage at the non-inverting input compared to the voltage at the inverting input. This is V1, this is V2. If V1 is greater than V2, the output is VCC approximately. If V1 is less than V2, the output is VEE. So this is the case where V1 is less than V2, so the output is VEE. VEE is connected to 0 volts here, so the output's approximately 0 volts. If these numbers were switched at the input, the output would be VCC, it would be 10 volts, but that's not the case here. Okay, so this is a comparator, and the result of the comparison is 0 volts at the output. All right, any questions on that? Oh, so let's see, I don't see how V2 is 5 volts. Yeah, let's, oh, and it's not obvious, I guess. So why is V2 5 volts? Let me see if I can draw this. I'll make an attempt here. If not, I'll switch to the whiteboard. Okay, so I'm going to isolate this part of the circuit. You have a 10 volt source, right? 10 volts that is connected to, right? Here's this point right here has a 3K ohm resistor. That's supposed to be a resistor. That's this top 3K ohm resistor. And then I have the bottom 3K ohm resistor, right? Right, so that's how these two resistors on the left are connected. I'm looking for the node voltage right there. This is V2. Okay, and V2 is the voltage between here and here. Okay, so you have 10 volts across two 3K ohm resistors. If you do voltage division, V2 is equal to 10 times 3 over 3 plus 3. Okay, so use voltage division to figure out this voltage. This voltage here is V2 because that's the voltage between here and here. Okay. And someone asks, how do we know it's a comparator and not an inverting comparator? You don't really have to know if this is what this circuit is called. You just have to, so all comparator circuits that you'll see will do this. V1 is always in our class, is always the voltage, the node voltage at the non-inverting input. V2 is always the node voltage at the inverting input. If V1 is greater than V2, the output is VCC. If V1 is less than V2, like it is here, the output is VEE. Okay. All right.
I have a quick question.
Go ahead.
Is it also a comparator since the top portion of it's are constantly held at 10 volts, or is that just something not to consider?
I mean, you could have a comparator that has different voltages for VCC compared to this 10 volts. Like you might have a different voltage across this voltage divider, and then you might have a different VCC value here that's not connected. It's a comparator because there is no negative feedback. And if there's no negative feedback in this class, it's a comparator. It's going to be comparing two voltages. So
Okay,
negative feedback, what it would do, negative feedback would drive the input differential voltage to be 0. Here, there's no negative feedback to do that. So the input differential voltage is actually -1 volts here. It's not 0, it's -1. The voltage between here and here would be, if you run a KCL or calculate the difference between node voltages like we did during node voltage analysis, you'd see this is -1 volt right there, not 0. Okay. All right, let's switch gears a little bit. And let's talk about what does a band pass filter do? We talked about filters in class a little bit, and you worked on a filter in lab. You built a filter in lab. So what does a band pass filter do? All right, let's talk about this. So an electrical filter in general passes some range of frequencies and blocks other ranges of frequencies. A band pass filter has a frequency response that looks like this. It has some pass band in the middle, above which frequencies are blocked and below which frequencies are blocked. And by blocked, I mean reduced in amplitude or attenuated. So if you have a low pass filter passes low frequencies. A high pass filter passes high frequencies. A band pass filter passes frequencies in the middle, right? So there's some middle band here. So a band pass filter blocks frequencies lower and higher than a pass band. All right. All right, let's move on to digital topics. What is the value of this number with this base in hexadecimal? All right, let's start this conversion between bases. So we have a binary number here, that's base 2. When you convert, one way to convert a binary number to a hexadecimal number is to look at groups of 4 bits or 4-bit words starting at the radix point, move left, move right, and then convert those 4-bit words into I like to first convert into a decimal number and then convert that decimal number into a hex digit. So starting at the radix point, if I go left and pick a group of 4 bits, a 4-bit word, that would be a 3 in decimal, right? 1 plus 2 is 3. If I move to the left one, that is a 14. So this would be 2 plus 4 plus 8 in decimal. That converts to an E, echo, in hexadecimal. And now I'm left over on the left side with 2 bits. Okay, what do I do with that? Well, I'm allowed to add leading digits. So leading zeros, I should say. So I add these leading zeros. That doesn't change the value of a number. It's like the number 6 and the number 06 in decimal, the same number. So this is a 2 in decimal and hex. Then I can go to the right of the radix point, and I have a 1 0, but I need 4 bits, so I can add trailing zeros, and 1 0 0 0 would be a decimal 8 and a hex 8. So my answer is 2E3.8. Okay. All right. And if you have any questions while I'm explaining these, you can throw them out in the chat. All right, let's move on to combinatorial logic. So you have this logic circuit. What Boolean expression directly represents that circuit above? Let's start talking about this. So I want to figure out what this end logical expression is. What is D equal to? So what I'm going to do is I'm going to start at the inputs and try to work my way to the right, building up the logical expression. Okay, so I have an OR gate here. Okay, and A and B are inputs to the OR gate, and OR gate is a logical addition. So here's a logical addition here. So that's A plus B right at that node right there. A plus B is the input to this inverter, this logic inverter. So I get A plus B inverse at the output. So the entire expression A plus B is inverted by that inverter. I have C coming in here into an inverter. So right after the inverter, I get the inverse of C. So now this AND gate is going to multiply together these quantities, A plus B inverse multiplied by C inverse. So A plus B inverse times C inverse, that's written right here. Okay. All right, someone asks in the chat, do we have to do a truth table? If for this problem, you don't have to do a truth table. In general, yes, the material for the exam includes truth tables, so you should know how to do, you should know what a truth table is for each gate. And we did an example of proving equivalence with truth tables. And what else do we do? We sum of products and product of sums for synthesis of logic circuits. So someone asks, wait, isn't A and C the same thing? Or does A imply the whole thing is inverted while C shows that each term is inverted? So A and C. Oh, I'm sorry, answer A and C. Sorry, I was looking at logic variables. Well, no, it's not the same thing. So answer A, we could draw out that circuit, but you would have to do the add and then the OR gate and then the AND gate and then invert the whole output. That would be a different logic circuit. Okay. So these A and C are not equivalent. Yeah. There's something called oh yeah, I see. So yeah, there's a separation here. So A and A plus B here, that's inverted. Separately, C is inverted. And in answer A, it's like you have an OR gate, and then you have that's an input to an AND gate with C as the other input, and then you invert the whole thing on the output. So you'd have some inverter at the output. Yeah, there's a gap there. That's right. I think you got it. Okay. Let's add a microcontroller into the mix. Okay, so this microcontroller uses 3-volt logic. You have these 3 bits out. You have an LED, another LED. This is the circuit. This P1 out, this is a byte that is programmed into an 8-bit output port. Okay, bit 0 is over here. Bit 1 is right next to it. Bit 2. Oh, wait, let's see. Oh, someone asks, do we know if the LED is on or off? Yeah. What's the value of P1 out when both LEDs are lit up? So both of these LEDs are on. Bit 0 is here. Bit 1 is here. Bit 2 is here. Bit 3 is here. And this is bit 7. Bits 3 through bit 7, they don't matter, right? So figure out if you were to program into the microcontroller a byte here, hex F9 or hex F8 or hex 06 or hex 8F, which one of those would light up both LEDs? All right, so let's work on this one. Okay, so we want to light up LED 1. LED 1 is in series with a resistor. We have ground on the right side of that resistor. That means we need 3 volts on the left at the anode of that LED in order to light up that LED. So I need 3 volts here. That means bit B0 is a 1. Okay. For LED 2, I want that LED to light up. I have 3 volts here applied through a resistor to the anode. That means I have to ground the cathode. I need 0 volts at the cathode. That's a logic 0. So I want a logic 0 at the output of this OR gate. To get a 0 out of an OR gate, you need both inputs to be zeros. So here's 0 and 0. That means that we have bit 0, bit 1, bit 2, 1, 0, 0. So 1, 0, 0, or bit 2 through bit 0, or 0, 0, 1. Okay, so these are the 3 bits I need, specifically those values, to light up those 2 LEDs. The other bits, I don't care, right? They could be all 1s, they could be all 0s, they could be any combination of 1s and 0s. So you got to figure out, well, which one of these answers would give me 0, 0, 1 in the least significant bits? Okay. So if I look at 4 bits at a time, and specifically, let's look at the right 4 bits because those are the ones that count here. I need a 1 in this least significant bit. So what could this nibble, this 4-bit word be? Well, it could either be 0, 0, 0, 1, which is a 1, or 1, 0, 0, 1, which is a 9. So the rightmost 4-bit word, nibble of the byte, has to be either a 1 or a 9. The other 4 bits, I don't care. Doesn't matter. They don't affect these LEDs. So I look for an answer over here that has either a 1 or a 9 as the right digit. And so it's going to be F9. Okay. So if you put F9 into this byte, connect the circuit to the microcontroller, both LEDs will light up.
I got a question about this one.
Yeah, go ahead.
How do we know that B1 and B2 would be 0? Because an OR gate also allows you to do B1 as 1 and B2 as 0, or the other way around. So how do we know that's like the exact right answer, since both would give you an output of 0?
Well, if for an OR gate, if either one of these inputs is a 1, the output will be a 1.
Oh wait, yeah, never mind.
Yep.
I just realized that. Never mind.
Mhm. Oh yeah, I see in the chat now. So yes, this lecture into office hours, this will be posted and linked to the Canvas page. So I'll stop at when we start talking about specific questions after the review problems. I won't post that, but I will post these review problems in a video. Okay. All right. Let's try this one. So you have this circuit with a transistor. X is an input, Y is an output. X and Y are 5-volt logic signals, and you have a 5-volt supply up here. So assume that logic level 1 is greater than 4 volts, logic level 0 is less than 0.3 volts. Assume when X is 1, the transistor is saturated. When X is 0, the transistor is in cutoff. If X is a logic level 1, then what is Y? All right, so let's work on this. If X is a logic level 1, which is 5 volts, that means we have base current flowing into this transistor. So IB is greater than 0. We're going to assume that this resistor, this base resistor, is designed such that it would cause that transistor to saturate. That's what these two bottom bullets are here, right? If X is 1, meaning there's base current, the transistor is saturated. If that transistor is saturated, a VCE sat is some low voltage. We assumed about 0.2 volts in this class. So that means the node voltage of Y is 0.2 volts, logic level 0. So the answer is 0. Okay, let's try this with, so same problem, but now I've changed X to be a 0. So try this. All right, so now if we set X to 0, we have 0 volts node voltage. That means we have no base current. The transistor is in cutoff. That means no collector current. If there's no collector current, then there's no current through this resistor. Then the voltage through that resistor, or not through, the voltage across that resistor is 0 volts. So there's 0 volts here. A KVL equation would show you that you have 5 volts here. That means Y is equal to 5 volts, logic level 1. So this is actually a logic inverter. On this page, on this slide, 0 volts gives you 1 volt, 0 volts input gives you I should say logic level 0 at the input gives you logic level 1 at the output. On the previous slide, logic level 1 at the input gave logic level 0 at the output. All right. Let's add a motor in. So what hex value will cause the motor to spin? All right, so let's take a look at this. To make this motor spin, I need to saturate this transistor. That means I need some positive voltage here to the left of the base resistor. Can't be 0. 0 volts at this point would cause the transistor to be in cutoff. The motor will not spin. No current would be going through it. So I need a 1 here. The 1 is an output of an AND gate. The way I get a 1 out of an AND gate is to have both inputs equal to 1. Okay. Continuing to the left, to get a 1 out of a logic inverter, I need a 0 at the input. To get a 0 here, I need a 0 at the output of the OR gate. That means I need 2 zeros at the inputs to the OR gate. Here's another OR gate output. I need that to be a 1. I have one of the inputs of the OR gate grounded, which means logic level 0. So in order to get a 1 out of this OR gate, I need the other input to be a 1. So 0, 0, 1, or if I read them in order, 1, 0, 0 in the binary word would be binary value, and that's a hex 4. It's a decimal 4 and a hex 4. Okay, so D. All right, moving a little more into motors. What technique is generally used to control the speed of a DC motor? So just like you used this same technique to control the brightness of an LED in lab, you can use that same technique to control the speed of a motor, and that's pulse width modulation. Okay. How about direction of a DC motor? How do you control direction of a DC motor? All right. So we talked about the way to control current, a way to control current through a DC motor or its direction, and that's with an H-bridge. An H-bridge looks something like this if you made it out of physical switches. Okay, so which switches need to be closed to cause the DC motor to spin in the forward direction, where if current goes left to right, the motor spins forward. If current goes right to left through that motor, we're going to define that as current for the reverse direction. Okay, so the answer is we want current flowing like this from the 5-volt source down to ground, left to right through the motor. So we have to close switches 1 and 4. All right. Okay, so we have a voltage Vx. Here's Vx versus time. Vx is a pulse width modulated voltage. What duty cycle of Vx will produce an average voltage of 3 volts? All right, so the duty cycle is defined to be the time that the voltage is high divided by the period of this square wave voltage. Okay, and you can figure out the average voltage by multiplying the peak voltage times the duty cycle for this square wave. So 3 is equal to 12 times the duty cycle. So 25% duty cycle will give you a 3 volt average voltage. All right. Okay, so we covered topics all the way from op amps through motors. That'll give you an idea of what the exam problems will cover. So the exam will be Tuesday, 5/7, no, 5/6. Oh, now I don't know. What's Tuesday? Let me check. Tuesday is 5/6, May 6th, from 7:30 to 10 p.m. So we've covered all the material for the class. In kind of closing, I hope that coming out of this class, when you look at some of these problems, you can remember back to when you started the class and, looking at some of these circuits like node voltage analysis problems or looking at, current sources and looking at voltage dividers and maybe even some of the digital topics and the op-amp problems, and especially relating lab to the class material. And knowing now how you can go into lab and perform electrical measurements and build on a breadboard and make circuits work that detect infrared light, right? So we've gone from basically like this is a volt, this is an amp, through go make an infrared remote control tester. So I hope you got a lot out of this class. So this will be the end of the last lecture. If you would like to stick around to talk during office hours, I'm going to end the video now and we'll continue on with office hours. So if you join, I'll see you there. And if not, I'll see you next time. Have a great night.